Hi everyone, my name is Makora. I'm one of the member of Group 9. So in our project, our mission was to build scalable school network that support teaching, testing, and administration without sacrificing visibility or control. We use a hierarchical core distribution, access design, role-based VLAN, and centralized services so that the network is reliable day by day and easy to operate. Why this matter? Classrooms need high density Wi-Fi, lab need stable throughput, admin offices must protect sensitive data. And plan network becomes slow and insecure. So our design fixes that with segmentation to reduce broadcast domain redundant length to maintain uptime and centralize monitoring to detect issue early. So what we built, we deploy core services in the server, VLAN for authentication, web and database services for application, file dash backup server for configuration and document storage, as well as monitoring server for NTP. So all devices send log, share health data, and synchronize time for accurate tracking. Monitoring in action. In package tracer, tooling and access port generates a, a Silog event with a timestamp. So the SNMP dashboard show interface counter raising during traffic simulation. This confirms our visibility into network performance and device status. Backup and recovery. Nightly, incremental, and weekly full backup are stored on the file dash backup server. Configuration are saved via TFPT and restore monthly for validation. This ensures rapid recovering for error or device failure. Security tied in. The AAA server enforces identity-based access while monitoring detect policy breach or failure. In production, we would upgrade to SNMPv3 and secure SMB for file sharing. These practices strengthen operational integrity. Result and next step. So as a result, we validated connectivity, segmentation, and observability, all centralized for efficiency. The next step is to migrate to SNMPv3, enhance file security, and add dashboard analytic for proactive maintenance. So basically, that what our project is about. Thank you for listening.
Hey everyone. So my name is Eugene Lee. So I'm in Group 9, and the topic we picked for this project is school uh, secure network. So the reason why we picked this topic because I think three of us are all graduate students, and this topic is the most relevant topic for us. So just a brief introduction on the parts I have done for this project. So those are the tasks I did for this project. So first is network design and beautification. Second, basic settings for all devices plus SSH and standard ACL for SSH. VLAN assignment plus all access and trunk ports on switches. STB port fast and the BDU guard configs on all access ports. Ether channel, subnetting and IP addressing, HSRP and inter VLAN routing on switches plus IP DHCP helper address, DCB server device config, OSPF on the firewall, routers and switches, firewall interface security zones and levels, and lastly, the wireless network configs. Okay, so now let's go to the Cisco packet tracer. So this is our project right here. So for the security level, we can see we have two firewalls, and this one is our inside campus area firewall, and this one is the outside firewall. So for this one, there are four interfaces. So this one, um, so we can see these two interfaces, gig 1, 2, and gig 1, 1 are connected to the our inside campus. So I set the security level for those two interfaces to be 0, since we totally trust the data from our inside network. And this one connect to outside. So I set the security level to be 100. And this one, I didn't set it's connect to our server, and I didn't set it to be 100 instead of setting to 70, which is not too strict. And same for this one right here. So those two interfaces connect to the inside network. I set the security level to be 0, and this one connect to outside network, and I set a security level to be 100. So now let's run the simulation and to see how it goes. Okay, I think it works pretty well. So the last thing I want to do is to do some testing and to see if our connections are valid. So I'm gonna choose the PC over here. So in the admission department, so I'm gonna choose this one. So we're gonna test three ping, I mean like three IP addresses. So one is 192.168.24.1. So this is our gateway IP address, and we can see we can connect it successfully. Second one is 10.10.10.5. So this one is our DNS IP address. And we also can connect to this one. Lastly, 10.10.10.26. This one connect to our inside firewall. So I just want to see if our PC can successfully reach to the inside firewall. Okay, we can see there is one request timeout, but this is pretty normal because if we run it again, and a has it will have 0% loss. Oh, it has a request timeout again, but if we try it again, yeah. So the reason why we have one single request timeout is because so if there's no recent traffic to the ASA inside IP, and the hosts or switches they may need to like resolve the MAC addresses. So the first ICMP gets dropped while the ARP completes, and the next one will be success. So all three IPs are connected, so that means our VLAN is successfully connected. So this is all the uh, content I need to present for my part, and thank you for watching.
Hello everyone, my name is Jinghua. In this video, I'm going to demonstrate three key parts of our medium-sized school network. First, the redundancy test using HSRP. Second, the dynamic IP allocation using DHCP. And finally, VLAN communication and isolation testing across VLANs 70, 80, 90, and 100. Okay, let's begin. First, I will demonstrate the redundancy between the two core multi-layer switches, BRMLS1 and BRMLS2, using HSRP, the Hot Standby Router Protocol. HSRP provides gateway redundancy for each VLANs, ensuring that if one core switch fails, the backup immediately takes over. Here, we can see that BRMLS1 is the active router for all VLANs 70, 80, 90, and 100, and BRMLS2 is the standby device. All VLANs on BRMLS2 are in standby state, which confirms that HSRP is operational. Now I'm simulating a failure on BRMLS1 by shutting down the VLAN 70 and VLAN 80 interfaces. This represents a partial core switch failure in Group A, VLAN 70 and 80. The standby switch, BRMLS2, should automatically take over the active role for these VLANs. After a few seconds, we can see that BRMLS2 has become the active gateway for VLAN 70 and VLAN 80, while VLAN 90 and 100 remain standby. This confirms that the HSRP failover is working correctly. Now I bring the interfaces back up on BRMLS1 within a few seconds. The primary switch automatically reclaims the active role for VLAN 70 and 80. The redundancy has been successfully tested, proving that our HSRP configuration ensures high availability in case of device failure. Next, let's verify DHCP dynamic IP assignment. We have configured DHCP pools for each VLANs on BRMLS1 and backup pools on BRMLS2. Here, we can see that several devices have already obtained addresses dynamically from the DHCP server. Now, I will open one of the clients in VLAN 70 called Labs PC1 and set its IP configuration to DHCP. After a few seconds, the PC automatically receives an IP address in the 192.168.26. range, with the default gateway 192.168.26.2. This confirms that the DHCP service for VLAN 70 is functioning properly. I will repeat the same on a PC in VLAN 90, the staff network, and it received an IP address in the 192.168.27. range, proving that each VLAN has its own DHCP scope. Finally, I will test communication between VLANs 70, 80, 90, and 100. Each VLAN has its own subnet, and we have applied ACL rules to isolate the groups. VLAN 70 and 80 from Group A, while VLAN 80 and 100 from Group B. First, I ping my own gateway 192.168.26.2. It succeeds. Then I try to ping 192.168.27.1 in Group B, and the request timeout. This proves that the ACL policies are correctly blocking traffic between groups. From a student VLAN in Group B, I can't reach the administration or faculty VLANs in Group A, but I can access the external DNS and web servers. This confirms that our VLAN segmentation and access control are functioning as designed. That's all, thank you.